So, suppose I have the following situation where I have to find the Laplace inverse of s divided by s square plus a square whole square. So, if I were to denote my function g, let us say g with a capital G, as e to the power s t s by s square plus a square whole square. Notice that g has a pole of order 2 at s equal to plus minus I a. So, these are poles of order 2. So, then if I were to evaluate the residue becomes limit s going to plus I a d d s. So, 1 by, well, the result says 1 by 2 minus 1 factorial, which is 1 factorial, times the first derivative with respect to s of s minus a s minus I a square of s e to the power s t divided by s minus I a square s plus I a square. Okay. So, if we were to take the derivative and evaluate this, I am going to get the answer as this is equal to t e to the power I a t by 4 I a. Similarly, if I were to find the residue, the second residue, that is at the second point of singularity. So, that becomes 1 by 2 minus 1 factorial, the first derivative of this following function s plus I a square, right. So, it becomes s times e to the power s t divided by s plus I a square s minus I a square, right, and what I get, that this is also equal to negative t e to the power negative I a t by 4 I a. Okay, so, finally, my result, my inverse transform, well, I get my inverse transform of this function s square plus a square to the power 2 will be the contour integral 1 by 2 pi c minus I infinity to c plus I infinity of g s ds, and that becomes the residue at r 1, the point 1, and plus the residue at point 2, and I get that this is also equal to 1 by 4 pi I a times t e to the power I a t minus e to the power minus I a t, and if I were to absorb this, I get that this is also equal to t by 2 a sin a t. Okay. So, you see that the method of contour integrals is quite handy, especially when we do not know how to find the Laplace inverse of some functions for functions which are other than the standard functions, let us say the functions which are given in my table. So, the contour integral is the most general way to find the inverse transform. Now, let us show a bit more complicated example of this inverse. So, here is one scenario, I need to find the Laplace transform. So, find the Laplace transform inverse of this function e to the power minus a square root s by s. So, of course, this is the standard integral, this is the integral that we have to evaluate 1 by 2 pi I c minus I infinity to c plus I infinity, and this becomes 1 by s e to the power s t minus a square root s times d s. Notice that this function is nothing but the convolution of these two functions. This was already done in my first example in today's lecture, that this is also equal to 1, the convolution of 1 with this function 1 by pi square root pi t cube, and I know that this is also equal to, I have found out that this convolution is equal to the error function complement of a by 2 square root t. Okay. So, I know the answer right before I start evaluating this integral. So, all I need to do is that I need to see that really my contour integral works well, and I need to show you that it indeed gives me this answer. Okay. So, let us now look at the contour here. So, notice that in this case my contour, so let me draw the integral, let me draw the curve here which on which I want to integrate. So, the curve here that I want to integrate is the following. So, this is the point C and this is from point R to R, where R goes from negative R to R, where this goes to minus infinity and this goes to infinity. And notice that in this inverse transform I have a square root function which is sitting, and also that we have 1 by s function which is in the, so s function which is sitting in the denominator. So, the point of 0, so s equal to 0 is a first order pole because of the fact that it appears in the denominator, and also this is also equal to, it is also a branch point. Why is that? Because notice that we have a square root function sitting in the numerator, and the moment we have a square root function, we know that there is a sudden jump of the values of s along the negative real axis. So, jump, there is a jump discontinuity across negative real of s. So, hence 0 s equals 0 is a first order pole and s equals 0 is also a branch point. So, if we were to draw this contour, we see that I have to evaluate the contour in such a way that I avoid this point 0 and go bypass it and go around it, and also avoid this branch cut, and I complete this contour. Okay. So, then let me say that these are now, there are now 5 line integrals that I have to evaluate. One is this line integral L. So, my let us say this is my integral I. So, my integral I is 1 by 2 pi, this is also the integral over line L, which is this integral, and this is also the integral over, let us say this integral is gamma, I denote this curve as gamma. So, I am travelling like this and I am travelling like this and I am travelling like this contour and this and this. So, then the second integral is over the curve gamma. Let us say this is my line L1 and this is my line L2. So, the other two lines are over integral line L1 plus integral over line L2 plus I call this curve as small gamma plus the integral over small gamma of the function that I have denoted. So, this is e to the power s t minus a square root s divided by s ds. So, that is there are these 5 integrals I am trying to evaluate over these 5 segments of the curve, which in which we have avoided the singularity as well as branch point. Now, Cauchy's residue theorem says that since this function is analytic inside this closed curve, because there is no singularity as such, we have avoided the singularity. So, this integral must give us 0. This is by Cauchy's residue theorem, the direct application of that theorem. Okay. So, I know that this is the integral, you see that this is the integral needed for us to solve. Okay. Now, let us look at this integral, the second one. So, let me the integral over gamma, it can be shown that, so let me say on the curve gamma. So, on the curve gamma, this is a curved part of the line integral. Let me just say that my variable s, so s is varying from in such a way that it lies on gamma, and s, the maximum value of s could be r, the minimum value of s is minus r. So, let us say that s is r e to the power I theta, right, and in that case my theta varies from pi by 2 to 3 pi by 2 in the limit r goes to infinity, right. We see that in the limit r goes to infinity, the theta is really from the positive imaginary axis to the negative imaginary axis. So, we can show that in this scenario my integral over gamma of, if I just plug this value of s and then of course evaluate this infinitesimal element ds, it is r is this value r is a constant. Eventually we take a limit of this constant, limit r tending to infinity. It is this variable which is changing with as s. So, the derivative of s is with respect to the derivative of theta. So, when we substitute this value in this integral, I am going to get something inside this integral such that what I see is that the real part of this thing inside this integral, the real part is negative. So, then as we take, so let me just repeat what I just said. So, on the curve gamma, my integral is such that the real part of this integral, the real part, so I can break it down into the real part and the imaginary part. The real part is such that this real part is negative, and when we take the limit r tending to infinity, so in the limiting case this vanishes, this real part vanishes, and in we can see that, well, to begin with we also had an exponential. So, we have an exponential function times some argument divided by some s, and when we plug in our substitution we can see that it becomes the following, it becomes e to the power real of something plus e to the power imaginary of something. It can be shown that the real part of that exponential is negative, and when we take r tending to infinity, then this goes to 0. So, in short, the integral over this curve gamma can be shown to be 0, and again this is via the direct application of Jordan's lemma, where we see that over the curved part this is 0. Now let us look at the integral over the line L1. Okay. So, again I am drawing this curve again. So, I have the following. So, I am just exaggerating my contour. So, I have line L1, this is line L2, this is gamma, this is line L, and this is small gamma. So, on L1 let me choose my variable s. So, s, so this time we are traversing from negative infinity to 0. So, let us choose my s to be r e to the power I pi, right. So, this is also equal to negative r. So, in the limit, so we see that s in the limit, s is actually a negative number here, right. So, but s is in general a complex variable. So, this will the value, by choosing this substitution, it will help us to take the square root properly. Now, notice that my integral over L1 becomes e to the power so s times t. So, e to the power s times t, where s is negative r. So, I get negative r times t, and the other one is plus, so minus what I had was a square root r e to the power I pi square root, right, and divided by r e to the power I pi, and then I get ds, which is e to the power I pi dr. So, I can cancel e to the power I pi, and all I am left with is the following integral from. So, we are traversing from negative infinity to 0, this integral becomes from negative infinity to 0 e to the power negative r t minus I. So, I get a complex number when I take the square root a square root r times 1 by r dr, right, and then I can do a proper substitution. I can substitute, replace r by minus r to change the limit of this integral to 0 to infinity, and this becomes exponential negative r t minus I a square root r by r dr. Similarly, on L2 I can do a similar change of variables. This time s will be from, my variable s will be this time r e to the power negative I pi. So, we see that L1 lies above the negative s axis and L2 lies below the negative s axis. So, hence there is this negative sign. So, when we substitute this value of s and evaluate the integral, I get the following expression. After all the simplification, the expression that I get is, this is e to the power minus r t plus I a square root r by r dr. Now, when I add this integral over L1 plus integral over L2, because that is what I have to eventually do, I add this one and I add this one, I get my answer to be equal to negative 2 I integral from 0 to infinity e to the power r t sin a square root r divided by r dr. So, then I can do a change of variables. Let me change x, replace x to be equal to square root r. So, instead of square root r, I am going to replace it with x. So, I get that this integral over L1 plus integral over L2 becomes negative 4 I integral from 0 to negative infinity e to the power negative x square t sin of a x divided by x dx. Okay. And then finally, so finally what I get is, now let us now, so I have evaluated over L, so that is my answer that I want, and I have evaluated the integral over gamma, capital gamma, and I have shown that this is equal to 0. I have evaluated the integral over L1 plus L2 and I have shown that this is equal to some non-zero value, some integral from 0 to negative infinity e to the power x square t sin a x divided by x dx, right, and then I have to see what is the integral over this small gamma, the small curve. So, again let me draw this curve quickly. So, I have this thing, right. So, I am talking about, so this is my curve, this is over L, this is over gamma, and this is the curve I am talking about is small gamma. So, integral over gamma that I get is 1 by 2 pi I integral over gamma, I get that this is equal to e to the power s t minus a square root s ds divided by s. So, notice that I am going to choose over gamma, you choose s equal to, let us say r e to the power I theta, where theta varies from, so it varies from negative pi, so negative pi, well not negative pi but plus pi. So, we are going clockwise. So, plus pi to negative pi, and also in this scenario when we want to come closer and closer to point 0, I have to take the limit r going to 0. Okay. So, this small semicircle is indeed very close to the point 0 in this limit r equal to 0. So, when we substitute this value, I get the following value of the integral. The integral becomes 2 pi I integral from plus pi to minus pi e to the power r t cos theta, right, minus a square root r cos theta by 2. So, that is my real part. So, times I d theta. So, the r cancels with the r down with this r here in this denominator of the s, and plus some imaginary part of the integral, right. So, here I have only taken the real part. So, notice for the imaginary part I am going to take the limit r going to 0. So, when I do that, in that scenario my imaginary part will disappear, and that can be shown for sin theta, right. So, in the imaginary part I am going to get sin theta, and in that scenario the second integral disappears. So, after taking the limit again, so in this, let us take the limit r going to 0, this limit here of this integral from plus pi to minus pi of exponential of this thing that I have written, right, and I d theta, and when I take the limit over this exponential, the value of this expression becomes identically equal to 0. So, this is 0, and then all I am left with is from pi to negative pi, this is 1 times I d theta, and then I am left with, well, there was a 2 pi I also. So, let me just write this 2 pi I. So, 1 by 2 pi I, and I am left with the value negative 1. So, finally what I have is, I need to post process this result a little bit more over L1 and L2. So, notice that I have this. So, let me just digress a little bit, because I want to evaluate this integral as well. So, I am slightly digressing from my question at hand, and I want to see what is the value of this integral from 0 to infinity. Notice that this integral is our standard integral, which is over the real axis. So, I am going to consider this integral. So, I know that the value is, let me choose alpha and beta to be positive, and I know that this is also equal to square root pi by 2 alpha e to the power minus beta square by alpha square. Okay. So, this is coming from standard calculus. So, students who want to see where we are getting this answer from should try to either derive it, they can substitute alpha times x to be y, and then use integration by parts, taking one of the functions as first, the other one as the second function, to arrive at this result. Okay. So, then let me call this as my result 1. So, I am going to integrate 1 with respect to the variable beta. So, this time my variable is not x, but my variable is beta. So, I am going to integrate with respect to beta, and what I get is, so a cos is going to bring out a sine for the integral. So, I get 1 half e to the power, so 0 to infinity e to the power negative x square alpha square sine 2 beta x divided by 2 x. So, let me just say that this is what I get by integration dx. So, this is integration with respect to beta, and that is also equal to square root pi by 2 alpha integral from 0 to beta e to the power negative beta square by alpha square d beta. So, when I do that, when I change my variable, I get that the right hand side is also the following. So, this is from beta by alpha e to the power negative u square du. So, where my variable u is beta by alpha. So, I have done a change of variable in my right hand side integral, and I know that the right hand side is nothing but equal to pi by 4 of the error function of beta by alpha. Okay. So, then coming back, notice that my integral over L1. So, I am coming back to my problem. My integral over L1 and L2 was negative 4I integral from 0 to negative infinity e to the power minus t x square sin a x by x dx, right. So, this becomes, so let me just choose my beta, to be, so 2 beta to be a, and also let me choose my alpha to be, well, so I choose my alpha to be x square. Okay. So, alpha square, well, we match x square with x square. So, I choose my alpha to be t, alpha square to be t. So, when I do that, my result shows me that this is also equal to 1 by 2 pi I error function of a by 2 square root t, and this follows from the result that I have shown above. So, finally, when I have to match all the integrals, so the answer that I get is the integral over L plus the integral over gamma plus the integral over L1 plus the integral over L2 plus the integral over capital gamma. All these integrals I am going to get, one of them was, so this one plus this one, I get that this is equal to, well, I have this is equal to 0. So, what I get is using Cauchy's residue theorem, right. So, what I have is that the integral over L will be negative of the integral over gamma plus negative of the integral over L2 L1, negative of the integral over L2 and negative of the integral over capital gamma. So, this was shown to be 0, this was shown to be equal to the error function negative of, this was shown to be negative of the negative, well, negative of the error function of a by square root t times 2, and here I had received that this was equal to negative of negative 1. So, this was shown to be minus 1. So, I get a plus 1. So, plus 1 with a negative sitting here. So, 1 minus the error function of this, and this is also equal to the error function complement of a by 2 square root t, which is what the answer that we saw in our earlier calculation. So, let me just end this lecture at this point. In the next lecture, I am going to provide you with some useful results known as the Tauberian theorems or the Watson's lemma, which helps us to calculate some of these inverse transforms in a very neat or a compact fashion. So, thank you very much.